Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So, my name is Tegar Taufik Rahman, and today I'm going to present my mini project about network flow. So, without further ado, let's get started. Enjoy. So, before we explain about the more advanced concept of network flow, so we need to understand or at least know about the definition of network flow itself. So, network flow is a directed graph where each edge has a non-negative capacity and each edge receives a flow. In the network flow theory, there is a source node called S in which the flow arrives and a sink node called T, which the flow leaves, and the amount of flow on each edge cannot exceed the capacity of the edge. So basically, if you have an edge from A to B and the capacity is 10, so you will not be able to put a value of the flow above A. So the value needs to be less or at least equal than the capacity. So the goal of network flow itself is to maximize the flow so the output has the same value with input, neither bigger nor less. So for the network flow problem, the setting is assume that given a directed graph G where each edge E has its own non-negative capacity, the capacity is bigger than each edge, and two special nodes, source called S and the sink called T, are given. So the problem is maximize the total amount of flow from S to T subject to two constraints. The first is the flow on edge doesn't exceed the capacity of C. So, and the second is for every node P is not equal with S or T, and the income is equal with the outcome of the flow. So basically this is just the goal of the network flow itself. So just like I explained to you in the previous slide, so the goal of the network flow is to find the maximum value of the flow from S to T. So this is the property of network flow. So the first is each edge has a non-negative capacity. So the edge has to be in a negative. So the each edge has to be in a positive value, not in negative value. And the second is if U to V is not in E, assume that capacity of U to V is equal to 0. So as you can see here, if you want to find the capacity of S to B, then the value is equal to 0 since there is no edge that is connecting directly from S to B. So the capacity from S to B is equal to 0. So just like that. So the third is we have a special node called a source S and the sink called T. And the next is assume that every vertex V in V is on same path and is on some path from S to T. So every vertex here, so, for example, like A, B, C, D, is in the some path from S to T. For example, here, so the capacity from S to A is equal to 16, but the capacity from A to S is equal to 0 since there is no edge that is connecting A to S. So the capacity from A to S is equal to 0. And the capacity from C to B is equal to 0. Just like we explained before. Just like from A to S is equal to 0. This is the condition that you need to satisfy in the network value. So the first is the capacity constraint, which stated that the flow has to be either smaller or equal to the capacity. So just like I explained to you before in the previous slide, so the value of the flow has to be either smaller or at least equal to the capacity. It cannot be bigger than the capacity. It will you will get an error if you do that. So and for the skew symmetry, it stated that the flow from U to V, U to V is equal to the minus of flow from V to U. So for example, the value of H from A to B is 9. So the value of flow from B to E is equal to minus 9. And the last one is the flow conservation. It stated that total input flow in each node has to be equal with the total output flow of the node, unless the S node is the source and the T node as a sink. So the total output has to be has to must have the same value as the input, like that. And this is the network flow example. This is the capacity in here. So from S to A, the capacity is 16. From S to C, capacity is 15. And this is the flow that is possible, that is possibly created from this network flow. So the S to A, the flow is 11, and from S to C, the flow is 12. So this is the example. So the flow from C to A is 1, and the capacity of C to A is 4. So the flow from A to C is -1, and the capacity from A to C is 10. And here the flow of B to S is 0. The flow from B to A is equal to -12. The flow from B to D is equal to -7. And the flow from B to T is equal to 19. Is equal to 19. So if you add these four numbers, it will equal to 0. So this is the total value of the flow. So we can get the value of the flow by this formula. So it is stated that we can get the total value of flow as leaving is equal to the value that arrived in T. So it's just the same as the input. The output must have the same value as the input. So this is the algorithm. So in order to compute the maximum flow we can get from the given net flow, then there is one algorithm that we can use. The name is for two-person algorithm. So I think it was found in 1956, and it was found by the four two-person. So that's why the name of this algorithm is for two-person algorithm. We will explain how it works on the next slide. But first, we need to explain about residual network, since the residual network is one of the things that we need to find at the post-focusing algorithm. So residual network is residual capacity of an edge in a network flow that can be kept by this following formula. So basically this formula is just the capacity from U to V is minus to the flow from U to V. So if there is an edge from A to B and the capacity of this edge is 10 and the flow of this edge is 9, so the residual network value is equal to 1. So this is the example of residual network. This is the flow. So for example, from S to V1, the flow is 11 and the capacity is 16. So the residual network will be like this. So the remainder of this minus operation will be 5, and it will be put above the 11 value. And the same thing also happened with S V2. And there is also an augmenting path. Augmenting path is a simple path from source to sink which do not include any cycles, and that pass only through positive weighted edge. And we can put more flow from source to sink to augmenting path. We call the maximum capacity by which we can increase the flow on P the residual capacity of P. So we can get the augmenting path value by using this formula. So actually the augmenting path, how to get the augmenting path is just we just find the minimum value from all possible residual networks. For example, this is the previous example from the previous slide. So as we can see here, the path from S to T, the first path that we get from S to T is through S to V2, V3, and T. So in this path, the most minimum value is from V2 and V3. So the value is 4. So since the 4 is the most minimum value at this augmenting path, so the augmenting path value is equal to 4. And this is how the algorithm works, just like what I explained you, just like what I promised in the previous slide. So while there exists a path P from S to T in the residual network, it will identify the augmenting path, and it will also increase the flow along that path, and it will repeat the steps until the path P from S to T it no longer exists. So this is the example of the problem. So we need to find the maximum flow of this graph. So as we can see here, the T, if you want to find the augmenting path, then we need to find it directly from T. So there is two directed edge, there is two connecting it. There's two edges that connected directly with T, it's B and D. So since the B value is smaller than D, then we use D. We use the B edge, and in B, since there's only one edge that is connected directly to B, which is A, so we use this A. And from A, there's only one edge that is connected, which is the S, so we use the S. So this is the residual graph, and this is the resulting network. So since we could get that the augmenting path from this path, this first path that we can get, is equal to 2, then we need to decrease the value that we pass through from the path is equals to -2. So for example here, so there is a flow that is equal to 2 that is connecting from B to T, and there is also A to B and S to A. So we can get that to this is the first flow that we can get, and the second is this is the first flow that we can get. So the first value of flow is equals to 0, but since we already get the augmented path value that's equal to 2, so we add it to 2, so the flow is now equals to 2. And the next one is the T, as you can see here, so there is only one that is connected directly to T, which is T, which has the value of 3, which has the value of 3 here, which has the value of 6, and to D there is only one edge that is connected directly to D, which is C, and the value is 6. And for C, there is two possibilities actually, from S or B, but because to S is shorter, so I'm going to use the S. And since the edge from S to C is equal to 3, which is the most minimum number that we can get on this augmenting path, so we're going to use this 3. And as you can see here, the T edge is divided into two branches, the 3 and 3, and it also happened in C to D. And as you can see here, the S to C edge is changed. The edge is just becoming C to S, not S to C anymore. And the flow is, since we get the total flow in the previous slide is equal to 2, then and after we get another new augmenting value which is equal to 3, so we're going to add these two numbers, which is equals to 5. And for the path 2, the path is SCDT. And the last path, and this is the third path, so the path from this graph is A, B, C, D, T. So as you can see in the previous in the previous slide, so the T will connect to D since the two since there is no possible way that we could connect to D, so the T will connect to D and the D will connect to C. And since there is no way that we could connect directly to S, so we need to turn to B. And after to B, we need to connect it to A, and then we finally reach the S. And the minimum value of this augmenting path is equal to 2, which is the value from the which is the value from B to A and A to S. So because 2 is the most minimum value, so we use 2. So since we already have 5 in our flow values, so we need to add it with 2, so it will become the 7. So since there is no possible way that we could get from T to S, so we will just stop here, and the resulting maximum flow that we could get from this graph is 7. And for the application, suppose that you want to ship natural gas from Jakarta to Semarang. There are pipes, each with a capacity. How can you send as much gas as possible from Bekasi to Semarang? The pipe flow from Bekasi to Semarang is described in the graph below. So this is the graph that describing the pipe from Bekasi to Semarang. So we need to So this is the implementation. So this is the code of Ford Fulkerson algorithm. So the implementation of the Ford Fulkerson algorithm is called Edmonds-Karp algorithm. It's not really the original Ford Fulkerson algorithm, but it made based on the Ford Fulkerson algorithm. It's kind of different with the original because in this algorithm, they use PFS to find the available path that we can use. This algorithm is called Edmonds-Karp algorithm. So the point is this BFS will find the available path that we can find as much as possible until there is no possible path that we could find. So it also in this BFS they also will find the residual network, and they will add the augmented value as well until they find the maximum flow right here. So the output of this program will be something like this. So in this program, the user will be asked to input the number of nodes that they want. In this case, based on the previous problem that we want to solve, we want to enter 6 number of nodes, and we also have to input the graph metric as well. And based on the problem that we want to solve, so the matrix we want to input has to be like this. So it's basically just a simple matrix table, simple ordinary matrix table. So in this table will represent each columns and row. So for example, this is the just for the column, this is just the 0 1 2 3 4 5 column, and for the row this is 0 1 2 3 4 5 row. So this 0 value here is basically just the multiplication between a matrix value from the row 0 and the column 0. So since the uh, since the starting edge doesn't have any directional edge, so we will just put here in the 0. And for the 10 here, it's just basically just the what is the uh, what is the edge that directed 0 to 1. So basically we just implemented this to 0, and Cirebon is 1, Bandung is 2, Tegal is 3, Purwokerto is 4, and Semarang is 5. So the edge value between Bekasi and Cirebon is equal to 10. So that's why this is equal to 10. And for the multiplication between the zeroth column and the second second row and the zero column, so I mean second column and zeroth row, so it's just like this. What is the value between Bekasi and Bandung? What is the value between 0 and 2? So the value is 8. So that's how it works. So if you have input all of the graph metrics, and you will be asked to enter the source of the graph as well. So the source of the graph will be equal to 1, which is Bekasi here, and the sink of the graph is equal to 6, which is Semarang here, and it will return the output. The output is 50, which is the right answer. So for the next topic is, does the 4-person algorithm is the best algorithm to calculate maximum flow? The answer is no, because there is another algorithm named Dinix algorithm, which is created by W.A. Dinix in 1970. It includes construction of level graphs and residual graphs and finding of augmenting path along with blocking flow. The time complexity of 4-person algorithm is O0 E plus Vf, which is simplified to O E multiplied by F, while the Dinix algorithm time complexity is equal to E P square. E multiplied by P square. So that's all for my presentation, and thank you for your attention and stay healthy.